Okay. Hello, everyone. So I think we can start from a short recall of our previous lecture. And uh, we considered units and dimensions last time. So we know now that units and dimensions, they are different things. They, in terms of dimensions, they represent some physical meaning of the quantity. So it provides some physical nature of the quantity we consider, like some physical parameter. We also, so units can be different. There are many systems of units. You can invent your one if you want. It just matter what is important. You need to do it systematically and be consistent when you apply certain units. You don't need to mess up with units. However, dimension is just the only option for physical parameter because it defines its physical nature. We learned also that if we have some equation, the dimensions of the right side of the equation should be equal to the dimension of the left side. And that is critical because we cannot compare parameters with different physical nature. So that doesn't make any sense. Taking this into account, we can always double check our derived equation. So we check what dimension we have of this unknown parameter, which we are looking in the located in the left side of equation with that equation which we derived in the right side. If these dimensions are different, then you need to do something to double check your results. Probably you made a mistake during the revision. If they are the same, there is a chance that your equation is correct, at least within some constant, with the accuracy of some constant. So also we considered some dimension analysis, which allows us to predict behavior of some unknown parameter with accuracy to certain constants. So we don't get the final analytically derived equation, but this equation gives us a chance to estimate the value and behavior of unknown parameter with accuracy of certain constant. So now, before we actually start working with mechanics, the object of our study during first half of the semester, we still need to make one step and in details consider such topic as vectors. So we know that physical quantities can be defined in like two groups. Can be scalar quantities and vector quantities. Scalar means they are defined only by number. They don't need any additional information. Number is enough. So for instance, some height. Your height is defined by some number and you don't provide anything else. Also, there is an option when we need to provide additional information, and that is direction. So in that case, when we have a quantity which requires both magnitude and direction, we have a vector. With vectors, we need to learn how to work because we need in the future on everyday basis multiply, sum up, subtract, multiply vectors. So we will go through all these steps today together in order to either refresh some of your memories about vector, or I believe maybe some of you will learn something new, which definitely will be very useful for you in the scope of this course and in the scope of all your career, because vectors, you will deal with them always. So let us start. And as an example of introducing a vector, let us consider some point A, point B, and imagine that we have somebody which moves from point A to point B with some curved trajectory. So it actually moved from point A to point B, but the length of this trajectory is called path of this body, which it made while traveling from point A to point B. However, there is another parameter as displacement, and path is just a number because it's just length of this trajectory. There is another parameter which is called displacement, so we will also discuss it a bit later. And this is a vector. Let's call it d vector, displacement vector. So in this case, it connects points A and point B in the shortest direction, means just a straight line between these 2 points. And it's already a vector quantity because it has magnitude. So it's defined by length of this straight line between 2 points A and B. So it will depend on relative orientation of point A and point B. And also it has a direction which also changes if we change position of point B with respect to point A. So in this case, we have an example of 2 quantities. First one is path, which is scalar. Another is a vector quantity, which is displacement. So next step, before we proceed further with vectors, we need to mention something about system of coordinates. So for instance, we have some system of coordinates x and y. So this is 2-dimensional system of coordinates, and here is some point, let's call it point P. So this point, like position of this point, can be defined by 2 numbers. It's actually it's x and y coordinates with respect to these axes x and y, which have the origin. So this is the origin of the system of coordinates. So we can define it with some x coordinate and y coordinate. Within this system of coordinates, these 2 numbers define the position of this point P. Now, there is another option to, and quite often is applied, to define this position of point P, and that is so-called polar system of coordinates. So what does it mean? We can form here some vector, which is called position vector. So y position vector, because it originates at the origin of the system of coordinates. So it's, and then its end is pointing to the point which of some point of our interest, which we want to quantify in terms of position in this system of coordinates. Now, what we have here, besides this position vector, we have also some angle alpha, which is formed between this position vector r and axis x. So now we have also 2 quantities. We have position vector and, well, position vector by itself automatically, as if we consider as a vector, automatically brings us 2 quantities, magnitude and position. So if we consider magnitude of this position vector and angle alpha, which defines position orientation of this position vector, we get 2 quantities which can describe position of any point in this polar system of coordinates. So how do we get it? We can write that x coordinate and y coordinate of this point P can be given as x is equal to position vector magnitude times cosinus alpha, and y is equal to position vector r times sinus alpha. So this is just very general information about systems of coordinates, which are most commonly used. So we either define it just by coordinate x and y, or in the scope of polar system of coordinates, we define it with magnitude of position vector and this angle alpha, which is formed between position vector and axis x. Okay, so with this, we can proceed towards some vectors. And here, let us consider two vectors, vector A and some vector B. So what is nice about vectors, we can also add and like subtract them from each other. So, and we need to do it quite often. So how do we add two vectors together? That is this simple, straightforward explanation, but not practical from some application because it will be difficult to realize. But we start from this simple explanation. So what we do, we just move this vector d so that its origin is aligned with the end of vector a. And when we do this, so when we have this vector b here already, this is our vector b, we can connect origin of vector a with the end of vector b with a new vector c, and that is the sum of vector a plus b. So quite straightforward and clear. However, we will see that there is another approach which is way more practical, and of course we will use that one in all our calculations, because here we just need to deal with some vector rearrangement that is only for purpose of demonstration. If, for instance, we have multiple vectors, so let's say we have some vector d as the sum of vector a, b, and c, for instance. So then we do the same procedure one step by step. So here is our vector a, then we align vector b, so its origin to the end of vector a, and the same we do for vector c. So here we have origin of vector a and end of vector c. We connect them with a new vector, which is the sum of all these three vectors. That also important to mention that if we change, for instance, b vector plus c vector, that, sorry, not c plus a vector, that will be still c vector. So it doesn't matter what is the order. Now let us consider how we subtract vectors. And in order to subtract vectors, there is such a term as negative vector. So imagine that we have again some vector a, and we create a new vector which is the same in magnitude. We don't change the magnitude, we only change the orientation to opposite. So it's just in opposite direction. So we can call this vector as minus a vector. In this case, if we want to have a difference between, for instance, vector b and vector a, so there will be some vector c, then it will be actually a sum between vector b and negative vector a. So it will be b vector plus minus a vector. So that's how we can deal with the subtraction of one vector from another vector. Another important feature which we need to highlight is when we multiply vector by some scalar number. And let's say we have again our old good friend vector a. Maybe let's do it here. So this is vector a. And we want to get some vector b which is equal to, let's say, 2 times vector A. In this case, when we multiply a vector by a scalar number, we increase only the magnitude of the vector. So we don't change the orientation. So that means we can draw here one additional part, the same vector A, one more, and next to it, just for visualization, we can show that a little bit already off. Can show, try to make it parallel, this vector B, which will have magnitude of twice vector A, and it will have the same orientation as vector A. So that is the result of multiplying a vector by a scalar number. So that, I believe, is quite clear. Now let us introduce very important vectors, so-called unit vectors. Any suggestions? What is a unit vector? Oh, you already know everything. Good. So let us introduce them. And definition, unit vector is a vector with unit magnitude. It just defines the orientation. So in order to make it introduce it, let us again consider two-dimensional system of coordinate first. Then we will go to 3. So this one is x, this one is y, and we are not enemies to ourselves. We want to define this orientation of unit vectors in that way which is convenient for us. So means that since we already have these two directions of axis x and axis y, we want to have them in the same directions. So here we have some unit vector I, and let it be here unit vector j. So they define the orientation of axis x and y. Now, when we have them, let us consider some vector A. So what can we do with this vector in order to make our life easier in terms of dealing with this vector? We split it in two components. One component of this vector will be along axis x. Another component will be along axis y. How do we split it? We have some projection of this vector A on axis x and y. So we consider here projection of vector A on axis x, A, x, and here projection will be A, y. Keep in mind that this ax and ay is just scalar numbers. It's just length of this projection of vector on axis x and y. And now we can just write the following. We have vector A, we can represent as the sum of two vectors. So this one is ax times I unit vector. So ax defines magnitude of this component, and I unit vector defines the orientation, which is along axis x. Then we have another component, ay times j unit vector. So this is how we represent a single vector, which can be randomly oriented with respect to this system of coordinates by two special vectors, sum of two special vectors, which are aligned exactly along axis x and y. So that really makes our life much easier, because now if we want to do some operations with vectors, and we already are familiar with unit vectors, we introduce here one more vector, let's say b, that will be bx times I vector, unit vector, plus by times j, unit vector. And now if we want to add them, so a vector plus b vector, that will be very easy. We don't need to think about any rearrangement of vectors, like end of vector with beginning of vector. We just add these scalar numbers which are staying next to the same unit vector. So it means that we have ax plus bx times I unit vector. This is the first component of the resultant vector. And the second component will be ay plus by times j unit vector. So this is the way how we add two vectors using this very nice feature as like unit vectors, representing them in terms of unit vectors, and that really makes it very practical and scalable. So we can deal with many vectors and calculate them using this approach without any problems. If we want to subtract, for instance, we have a vector minus b vector, that will be ax minus bx times I unit vector plus ay minus by times j unit vector. So this is about doing these simple operations plus minus vector. When we represent them in terms of unit vectors, it becomes way more practical. We also need, besides adding vectors and subtracting, we also need to multiply vectors. And there are two options to multiply vectors. That is dot product and cross product. So let us first start with dot product. And let us highlight first that dot product of two vectors gives us, as a result, some scalar number. So it means we go from two vectors to scalar. As an example, of course, we will discuss this in details, but as an example to make it clear, for instance, when we have two vectors, one is force, vector force, which is exerted on some body, and another is displacement of this body. So we have two vectors because force and displacement are vectors, and we want to calculate work done by this force moving this body. So in that case, we deal with two vectors as initial information, and we use this dot product. That dot product gives us a scalar number, which is work. Work is a scalar. It doesn't have direction. It's defined just by a number. So that is some example of application of dot product. And how we work with it. So in this case, we probably can already introduce system of coordinates, like three-dimensional system of coordinates. And so it will be x, y, z. Here we have I unit vector, j unit vector, and k unit vector. So if we have some vector a in three-dimensional system of coordinates, it will be ax times I unit vector plus ay times j unit vector plus AZ times K unit vector. Next, we provide information about vector B, which we need also for our dot product. Will be Bx times I unit vector plus By times J unit vector plus Bz times K unit vector. So now we want to get the dot product of two vectors, A vector and B vector. And that will be AX times BX plus AY times BY plus AZ times BZ. Or we can represent it as product of the magnitudes of vector A and B times cosinus alpha. Alpha is the angle between two vectors A and B, which we use for this dot product. So in this case, it is quite straightforward. You see that here we don't have any unit vectors, means that this sum of three terms gives us just a scalar number. There is no information about direction. So with dot product is like everything is clear. Now let us go for cross product, which is kind of more interesting. And first, let us consider magnitude of cross product. So that will be vector A cross product vector B. That will be equal to product of magnitudes of vector A and B, A vector magnitude times B vector magnitude times sinus angle alpha between these two vectors. However, this is only the magnitude. And the thing is that cross product, and this is the key difference between dot and cross product, it gives us not a scalar cross product, it gives us a vector. And this vector, first of all, we need to know how we define the orientation of this vector, and also how we get magnitude of this vector, and how we do it in a practical way for real calculations. So first, let us just schematically define the orientation of this resultant vector, which we get after cross product of two vectors. Let us have two vectors, A and B. So something like this. So this is vector A, this is vector B. So imagine that we have some plane. So it's not drawn in plane of our board. So we will consider this probably for better understanding also. But now we have just some plane in three-dimensional case, which goes through vector A and B. And now we want to have cross product of these two vectors. Let's say we want to find vector A cross product vector B. In that case, what we do, there is a right hand rule, so-called. We, with our right hand, twist our right hand in that way that with four fingers we first cross vector A, which stands first in this cross product. Then we cross vector B. When we do this direct, like this orientation, our sum of the right hand will show us the direction of the product, cross product of A vector and B vector. So it will be always perpendicular to both vector A and B, means the cross product of vector A and B will be perpendicular to the plane which goes through these vectors A and B. So means that we will get here some vector C, and this vector C is equal to the cross product of vector A and B. So for maybe better understanding, let us consider two vectors. It will be A vector and B vector, which are drawn in the plane of y portion. So now, by applying this right-hand rule, we arrange our right hand in that way that we first, so we calculate A times B, like cross product B. So our fingers cross first, four fingers cross vector A, then cross vector B, and our thumb is showing the direction of the resultant cross product vector. And that will be perpendicular to this plane of the whiteboard from you in that direction. Now, important thing, so that we were talking about A cross product B. If we change their position, B cross product A, that will be already a different story. Because we have first vector B, so we need to arrange in a different way so that our fingers, four fingers, cross first vector B and then cross vector A. And in this case, vector C, which is the cross product of vector A and B, will be oriented perpendicular again to this plane of the whiteboard, but towards your direction. So it will be opposite direction in the initial case. So that please remember. So you can flip vectors in dot product. That doesn't make any difference. But in cross product, that already gives an opposite direction of the result. So with magnitude of the cross product and its orientation on qualitative level, we kind of figure out. So we know with this right-hand rule how to define the orientation. Now, in order to go to this final form, how we calculate cross product of two vectors, we need to introduce in the like in between some consideration of cross products of unit vectors. Let us come back to this three-dimensional system of coordinates. Will be x, y, and z. Let us make it colorful. So here we have unit vector I, unit vector j, and unit vector k. So these are unit vectors, but nothing stops us from having cross products of these unit vectors. They are just regular vectors, but with magnitude of unity. So we can apply to them any rules which we apply to any other vectors. It's just convenient because they are, first of all, unit vectors. They have unity magnitude. And what is also very important, they are oriented perpendicularly to each other. So now let us make such a table. 1, 2, 3, and here will be, yes. That depends if you have a vector cross product b vector, then you are right. If you have b vector cross product a vector, then it should be in the opposite. It should go from b vector first and then a vector. Everything defined what stands first, a or b. So here we have our table. Let us put here I unit vector. Here is j unit vector. Here is k unit vector. The same here, I unit vector, j unit vector, k unit vector. So now let us see what we get when we have cross product of these unit vectors. First, let us consider what we have here. We have I unit vector cross product I unit vector. Any suggestions? What is the magnitude of cross product? We had it. It's zero. So we have the sinus alpha. What is the angle between I unit vector and I unit vector? Zero. Sinus zero will give zero and means that we have zero. So this will be zero. So means that when we multiply unit vector, the cross product, have cross product of unit vector by itself, we get zero. Following this approach, already can claim that here we also have zeros because for both cases we multiply unit vector by itself. So this will be 0 and 0. So now we have already 3 components of this table. We need to figure out the rest 6. So let us consider I cross product j. What will be here? T or 1 is just scalar. So in terms of magnitude, you are right. It will be everywhere 1 besides the zeros. But we want to get, because cross product gives vector, so we need to end up with a vector. So if we look here, we have I times j. So we apply this right hand rule and we cross first with 4 fingers vector I, then we rotate to cross vector j, and our sum is showing this direction of vector k. So we can write here, this is vector, unit vector k. Let's go further and let's see I times k. Okay, so here is important thing, because when we have I times k, so that should be something like this. We rotate our hand, right hand like this. So I'm not so flexible, but this should result in the direction which is opposite to axis y. So it will go here. And since it goes here, it will be opposite direction of unit vector j. That's why we write in this last cell minus j. Okay, so following the same approach, we can fill out all the rest of these empty cells. So j unit vector times I unit vector will give us minus k unit vector. J times k unit vector will give us I unit vector. Then we have k unit vectors cross product I, that will be j. And last will be minus I unit vector. So now we have this table. You can keep it in mind, but don't need to remember it. You just apply this right-hand rule and always can define what you get after having this cross product of any unit vectors, any combination of unit vectors. Now, after we are done with this, we can try to get the analytical calculation of the cross product of two vectors in three-dimensional space. So let us give here vector A it will be ax times I unit vector plus ay times j unit vector plus az times k unit vector. Similar, we write for vector b. This will be bx times I unit vector plus by times j unit vector plus bz k unit vector. So we want to get the equation which gives us a possibility to find both magnitude and orientation of cross product of vector a and b. So we have a vector cross product b vector. This will be equal to, so we actually need to multiply this by this. So how it works, we just pick up one term from the first parenthesis, multiply them by each of terms in the second parenthesis, and repeat it for each term in the first parenthesis, and sum up everything together. So let us write it here. So it will be ax times bx, and here, so we multiply two scalar components, and here we need to multiply it by cross product of unit vectors which stay next to these scalars, ax and bx. And what is staying here is I unit vector. So we have I unit vector cross product I unit vector. Now, next term will be ax times by, and here we have cross product of I unit vector and j unit vector. Is it clear now? Everything is clear. Okay. So we continue. We write ax times bz, and this will be I unit vector times k unit vector. So that are our first term from first parenthesis. We need to go to second term now. It will be ay times bx, and this is j unit vector cross product I unit vector plus ay times by j unit vector cross product j unit vector plus ay times bz j unit vector cross product k unit vector plus, now the last term here, az times k unit vector. So it will be az times bx. Here is k unit vector times I unit vector plus az times by k unit vector cross product j unit vector plus az times bz k unit vector cross product k unit vector. Okay, we are done with this. So quite bulky, but we can make some order here. So that will be equal. So here we see, first of all, we pay attention to these guys. Yes. So we can cancel out these terms because they are equal to 0. So now if we look at our table and substitute instead of each of these cross product its value, so we can double check, for instance, I unit vectors times j unit vector. So we look here, I times j unit vector should give us k unit vector. So it means this guy should be equal to k unit vector. So we do this for all terms. Yeah, probably we don't have enough time, but it's clear how we follow. So let's say I times k unit vector. We look here in this table, I times k unit vector, that is minus g unit vector, and j unit vector. And then we follow like this to all of these products which are not equal to 0, which we don't cancel out. As a result, we can group those terms which have the same unit vectors next to them. So eventually we get the following. So it will be a y times b z minus a z times by times I unit vector. Here we put minus. It will be a x times b z minus a z times bx times j unit vector plus ax times by minus ay times bx, and this times k unit vector. So what we got here? So we see here that we have a cross product of two vectors, a cross product b vector, and eventually we have three components. So vector which is represented by three components, a line along axis x, y, and z, and these are the magnitudes. In the parentheses, these are the magnitude of these components of the resultant vector, which is the product of cross product of vector A and B in three-dimensional space. That means that with this approach, we get both information about magnitude of the resultant vector of this cross product and its orientation. So if you check a bit further, like look at this solution, that could be represented as the determinant of a 3 by 3 matrix. So maybe you are familiar with this. If not, you will definitely deal with this in linear algebra. So we can represent A vector cross B vector as determinant of such a matrix. It is I unit vector, j unit vector, k unit vector. Here we have a x, a y, and a z. And here we have components for the second vector here in this cross product, by and bz. So just keep in mind that when you get this determinant, you need to remember about this minus, because this minus originates from the fact, if we look at this table, the fact that we have sometimes negative values of cross product of two unit vectors, depending on their orientation with respect to each other. So in that case, just because of that, we have here this minus, and it should be taken into account. But this is the most like common form of giving the equation, like approach to calculate the orientation and magnitude of cross product of two vectors in three-dimensional space. So if you have any questions, you're welcome. This is pretty much everything what we wanted to discuss. Please go through this material. This is important because this will be with you during everyday life for many, many years. Thank you very much for your attention, and see you on Monday. Have a great weekend.